Hi, in this video we're going to go over section 12.3 of Stewart, which is about dot products. This will be part 1. We're just going to go over the basics. So the idea of a dot product is we're going to add the products of corresponding components. So it's going to be one of two products we learn for vectors. And this one's going to just take each component, multiply them, and then add the results up. A key thing to remember here is this will gives a scalar. This will give us a scalar. Or just a number. It will no longer be a vector. And an example with just numbers, if vector A is A1, A2, A3, and vector B is B1, B2, B3, A dot B, so this is a dot product of two vectors. We're going to be very careful with using a dot for multiplication from here on out. It would just be A1 times B1, the product of the first components, plus A2 times B2, the product of the second components, plus A3 times B3, the product of the third component. We'll do an example with numbers. And you should try this out. You should try it out and see if you understand it so far. It shouldn't be that bad. 2i minus 3j plus k. And w negative I plus 2j minus 2k. Can you find the dot product of v with w? Go ahead and try it out. 3, 2, 1. You should have negative 2 minus 6 minus 2. So this dot product is negative 10, which means what? That's going to be a topic for the next video, I believe. So we're just going to deal with it for now. But it is a scalar. That's one thing I really want to be clear about. This is just a number. We've lost the idea of being a vector. It's not 10i, it's not 10j, it's not 10k. It's just negative 10. I want to go over some of the key properties here. A lot of these will be familiar and make sense from the old multiplication you know for scalars. If I take v dot w, that would be the same as w dot v. The order we multiply them does not matter. We'll get the same result. Commutativity is what this property is called. Distribution. We're able to distribute vector multiplication, dot product multiplication over vector addition. Wow, I can't talk. So we would get v dot u plus v dot w. Okay, just like how distribution used to work. This next one's a little strange, be pretty common. It's that scalars can move around here. Scalars are commutative. So if I'm trying to scale v and then do the dot product, that's going to be the same as doing the dot product between v and scaling up w. Or it'll be the same as multiplying the scalar I'm getting out of v dot w with the scalar c. So again, remember v dot w there would be a scalar, and we're just multiplying that scalar times this other constant c. Notice that c is a scalar constant. It does not have a hat. It does not have a hat. It means it's a scalar. 4. If I take the 0 vector, which you should recall is the vector with all 0 components, and I dot product it with v, I'm getting the number 0. I'll say this. Recall 0 vector is 0, 0, 0. The vector, all coordinates are 0. And 5, last but certainly not least, the most important property we'll be talking about. If I do a dot product of v with itself, what it's giving me is the length squared. I'm going to prove that algebraically really quick. If I have v1, v2, v3, dot product with itself, v1, v2, v3, what I'm getting is v1 squared plus v2 squared plus v3 squared. You might be like, well, I don't know. That looks unfamiliar to me. Well, what's the length of v? If you remember how to do the length of v with that, it would be the square root of all that. And so you should see the connection there, right? Let's just do an example of some vector math addition. Sorry, some vector dot product math. If I have v is the vector 1, -3, 2, and w is the vector -2, 4, 1, and u is the vector, let's change it up on u, 2i minus 4j plus k. Can you right now find v dot w plus u? There's two ways to do that, hint. And 2, v dot w times u. Notice for that second part there, there's no dot anymore. Think about why. Try to get answers for 1 and 2 right now. 3, 2, 1. I'm going to assume you tried it out. So for the first one, there's two methods. Option 1, we can do v dot w times w plus u. Sorry, I can talk. W plus u would be 0, 0, 2. And if I do those dot products, I would get 0 plus 0 plus 4, or 4. That's if you just added first and then did the dot product. But you should also know, using the property method 2, we could distribute v dot w plus v dot u. So v dot w, you could have gotten -2 minus 12 plus 2 plus v dot u, 2 plus 12 plus 2. Which is, of course, you'll see a lot of cancellations there and get 4 also. For number 2, there really isn't anything else to do besides take that dot product first, which we just saw from above is -14 plus 2, which is -12. And then it's multiplying with this vector 2i minus 4j plus k. So what do you do here? Is it another dot product? No. This is a product of a scalar times a vector. So it's just going to scale up the vector by that number, -12. And that's all there is to it. Like I said, this was part 1, the basics. Please watch the next one to see more interesting stuff. Thanks for watching. Bye.